Hey everybody, we are going through this problem about figuring out all of the different voltages and currents through this circuit. To do this, we'll need to understand some things about the current law and the voltage law, and I'm excited to go over them. So, at first glance, this problem is complex to figure out all the voltages and the currents at different locations in this circuit. But we have some tips for making this problem a little easier. One, I can say, you know what, let's draw this. And instead of saying this is a 4 ohm and a 2 ohm resistor right here, let's combine them into one. Because they have an equivalent resistance. They are in series. And for all series resistors, you can just add up those resistances to get your equivalent resistance. R equivalent equals R1 plus R2 plus R3 plus ... forever and ever. So a 4 and a 2 ohm resistor are equivalent to a 6 ohm resistor. These two resistors are not in series. It's not the same current that's traveling through this resistor that's traveling through this resistor. That's what's happening here. Same current, but this split, called a junction, means that we're going to see some of the current travel across the 3 ohm resistor and others keep going towards the 6 ohm resistor. We can combine parallel resistors by adding them up in a way that actually makes the equivalent resistance smaller. And you can do that like this. 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3, if there are 3, ... forever and ever. And it turns out when you do that with the 3 ohm resistor, I'll show that work. It becomes 1 over 3 ohms plus 1 over 6 ohms equals 1 over R equivalent. Or these combined mean 1 over 2 ohms equals 1 over R equivalent. But do not leave your answer as 1/2, because this is not the equivalent resistance. 1/2 right there. That ohms is on the bottom. This value is measured in 1 over ohms. The equivalent resistance, taking the inverse of both sides, is 2 ohms. So I can go ahead and put that right there. And I've just made this circuit a lot easier. Just like in algebra, when you simplify, I've taken this circuit and made it a little easier to look at. I'm going to do this again, because now what I have is this 16-volt battery in series with a 6 ohm and 2 ohm resistor. And I can combine them to say, you know what, they're equivalent to an 8 ohm resistor. All the current that travels through here is all the current that travels through here. And even though this circuit isn't really an 8 ohm resistor, it has an equivalent resistance to this 8 ohms. Now the question is, all right, let's go back. Let's say, what information do I know about this simplified circuit? Well, one thing that I know is that for any loop of a closed wire, if I look at this, I have current traveling through this whole thing. The voltage law, which is sometimes described as Kirchhoff's voltage law, also called the loop rule, says the sum of the volts in any closed loop must be 0. Meaning that if I go up 16 volts at this location, as I go through the loop, I'm going to go down 16 volts. That has to happen in a circuit. Whatever volts you go up, you have to go down to. And it doesn't matter if you call this positive 8 volts and negative 8 volts or 0 volts and 16. You're going up 16 volts of potential. So throughout the entire circuit, you have to lose those 16 volts of potential. This is a different way of saying that energy is conserved in this circuit. All the potential energy that these charges have gets used up and turned into heat, thermal energy across these resistors. That's the only place where we're going to lose any potential in this circuit is across these resistors, because we'll assume that these wires are perfect and have no resistance in this problem. So if I call this the 0 volt line and this the 16 volt line, I can say the potential here is 16 volts, 16 volts, 16 volts, 16 volts. And then that means there must be a drop right here that gets me to 0 volts. So the drop across here is 16 volts. Some people say negative 16 volts, but whenever we're going across a resistor, we lose potential when our current's going that way. So that is a drop of 16 volts right there. Now, I know something about this. I know the voltage drop across that resistor, and I know the resistance of that resistor. That means I can use Ohm's law, I equals delta V over R, to figure out the current in there. And this is a 16 volt drop over an 8 ohm resistor. And that tells me the current through this resistor is 2 amps. And because there's no junctions, places where the current could split, the current right here is 2 amps, and the current right here is 2 amps, and the current through the battery is 2 amps. Everything here is in series. And for series resistors, to write this again right here, or series anything, really, we've already said that the equivalent resistance is equal to the sum of the resistances, R1 plus R2 plus R3 plus dot, dot, dot. But one thing that's also true is that the current, the total current, is the same, is equal to I1, is equal to I2, is equal to I3. If you have 3 resistors in series, they're always going to have the same current in them. Now, if I go up from here, because I know everything about this circuit, I know the voltage, the current, the resistance. If I go up, this circuit is equivalent to this one. And that means that this 2 amps of current is still the current at all locations here. All the charges that are moving in this circuit feel the traffic jam, are affected by the traffic jam that happen in these 2 resistors, and they're all slowed down with an equivalent resistance of 8 ohms. That means that now I know the current in this resistor and the resistance of this resistor. I can draw this little curved line to represent the potential here and here. The difference between them must be delta V equals I times R, or 2 amps times 6 ohms, which is a drop of 12 volts. And that means across here, this must be a drop of 4 volts for 2 reasons. One, that's Ohm's law. Delta V equals I times R. 2 amps times 2 ohms is 4 volts. And this is something we already knew about the voltage law. The sum of the volts in this loop must be 0. And if I go up 16, I'm going to drop 12, and I have to drop 4 to get back down to 0 volts. Because the potential here is 0 volts, 0 volts, 0 volts. And the potential here is 16 volts, 16 volts. And the potential here is 4 volts, because we dropped that 12. So that is the voltage law and the current law in action, and Ohm's law. Another thing about series resistor is the total voltage across them is equal to the sum of all the voltages across all the resistors, plus dot, dot, dot. That there's a total drop of 16 volts, which is a drop of 12 volts, plus a drop of 4 volts. Going back up, I now realize that this circuit had more to it. This wasn't really a 6 ohm resistor. This was a 4 and a 2 ohm resistor. But the current is the same. Those are in series. And the drop across this one, quick little Ohm's law, delta V equals I times R, means that this must be an 8 volt drop and this must be a 4 volt drop. And that makes sense because I said that this was a total of a 12 volt drop and this is equivalent to this. So there's our 12 volt drop just split over the 4 ohm and the 2 ohm resistor. Neat little proportions, you realize that this resistor is twice the resistance, so it takes twice the voltage drop. You lose twice as much energy going through this one as this one. And this creates twice as much thermal energy in the same amount of time as this one does. Now, let's take a look at this parallel one. There's something I know about this parallel one, that at this point, I've gained 16 volts in my circuit if we start right here, and then I go 8 volt drop, 4 volt drop. And that means both of these, either way you take, has to be a 4 volt drop. Whether the charges went through this resistor or this resistor, they would both have to experience the same 4 volt drop because we have to get back to 0 volts at the end. All the charges go through this one. All of them have an 8 volt drop, all of them have a 4 volt drop, and then they decide by being pushed from one way or the other by the electron behind it, whether they're going to get forced through here or through here. And that creates a 4 volt drop and a 4 volt drop through either and both of those resistors. Now the question is, what's the current here? Well, it's not going to be 2 amps anymore because this 2 amp current splits at this junction, as we already said. Some of the current goes down here and some of the current goes down here. Conceptually, I can see that more of the current is going to go through this resistor than this resistor. That's because this one has a less resistance. The charges are going to be more likely to travel through here. There's less of a traffic jam going on, and more of a traffic jam going on right here. How to figure out how much current there is, there's a few ways I could do this. One is with Ohm's law, the voltage divided by the current. 4 volts divided by 6 ohms tells me that this is going to be 0.67 amps. And then Ohm's law here tells me this would be 1.3 amps of current. I could have also figured that out by looking at a ratio here, realizing that this is twice as much resistance as this resistor is right here. So that 2 amps is going to split up, and twice as much current has to go through here than goes through here. And that's the way the math works out. Twice as much current goes through here, twice as much resistance here. So the currents and the resistances go together, because I times R here has to equal I times R here, because in parallel, these have to have the same voltage. Reviewing that idea, for parallel resistors, we've seen how we can add up their equivalent resistance. 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3 plus dot, dot, dot. The current in parallel resistors is equal to I1 plus I2 plus I3 plus dot, dot, dot. They're not the same. But if you add them all up, if you add up this 1.33 amps and this 0.67 amps, it gives you exactly what we should when they come back together, this 2 amps of current. And then the voltage total is the same across parallel resistors. That all resistors in parallel are going to have the same volts. This is a 4 volt drop and this is a 4 volt drop. So that's a neat thing to know about series and parallel resistors. And as you work with this stuff, keep in mind that all your rules, that you can keep track of the voltage law, things we know about series resistor and things we know about parallel resistors. One last thing is the current law. Let me just write it out. That says I into any junction equals I out. And that's best illustrated up here, where 2 amps flows into this junction, and we get 1.33 going this way, 0.67 going this way. But that is still the total 2 amps, the same we had here. Because you can't destroy charge, you can't create charge. And that same charge flow has to happen here and here, because that's what current is. The rate of flow of charge, the amount of charge flowing past a point in a given amount of time. So, this is how we work through complex circuits. You make them really simple, and then use the things we know about circuits to build those ideas back up. Happy studying!